Now I'm delighted to introduce our speaker, Philip Harris. Philip joined the MIT faculty in 2017. Born in Sao Paulo, he received his BS in physics from Caltech in 2005 and his PhD from MIT in 2011 on research performed at CERN with the Large Hadron Collider. From 2011 to 2013, Philip was a CERN fellow working on the Higgs discovery. From 2014 to 17, he was a CERN staff scientist working on dark matter searches at the CMS experiment. Super cool. Philip is one of the founders of the Fast Machine Learning Organization. Also, he's currently the experimental coordinator of IFI, which is the Institute for AI and Fundamental Interactions, and is the deputy director for the Accelerated Artificial Intelligence Algorithms for Data-Driven Discovery, or A3D3 Institute. Please join me in giving a warm welcome to Philip Harris. Philip, without further ado, the floor is yours.
All right, thank you, and thanks for the nice introduction. So, yeah, I'm going to talk about high energy physics. Actually, this is kind of a misnomer. I'm going to actually talk about kind of lots of different, ideas and where AI has really played a major role in physics, and actually talk about gravitational waves as well. So let me kind of start with the Higgs discovery. So at the time of the Higgs discovery, we were mostly doing, kind of rule-based physics. It was an exciting time. Actually, that's me over there in the photo. So I was very much involved. And, we made this discovery, and we made these plots like this. So these are the kind of p-value, the probability of, fluctuation looking like a Higgs boson. And we saw, with two experiments, the ATLAS experiment, the CMS experiment, something like 5 standard deviations from 0. Now, what people didn't notice in that experiment was this dashed line. So this dashed line is actually the expected sensitivity. So this is the kind of expected p-value you would have had if you had a Higgs boson. And what you see is, well, the ATLAS experiment was about 4.5 standard deviations, whereas the CMS experiment was about 6 standard deviations. And there was a big difference, right? They both claimed discovery, both, saw it, but there was actually a difference in the sensitivity. And what was the difference? Well, it turns out the difference was actually machine learning. So if you look in the kind of diphoton channel, the CMS experiment used machine learning there. If you looked at some of the other channels, so for example, the type W boson, there was a machine learning kind of used here, and lots of other things. And actually, this is one of my algorithms right here. But suffice it to say, the other experiment, ATLAS, didn't do that. And that's really the kind of main difference for the sensitivity. So at the time, right, we already had kind of glimpses and ideas that kind of machine learning based analysis was definitely the kind of direction to go. And then kind of in the mid 2010s, once the rise of software frameworks, GPUs, all of this use accelerated very rapidly, and it's kind of changed the kind of dynamic. And just to kind of summarize what happened in kind of the, since 2016 to like 2022, is we started adopting as much machine learning developments as we could. Right? So we started when CNNs were all the craze, we started making images. The problem is that at Collider, right, images are not Lorentz invariant objects. And so you can't take an image and boost it and have it look the same. And so this ended up having problems. We started feeding particles into recursive neural networks, right? And trying to do things kind of similar to that when, GRUs and LSTMs were all the rage. And then when graph neural networks came about, like, 2 years later, we switched to graphs, and now we could deal with particle correlations. And not so long after that, we realized self-attention would be useful as well. And so, we switched to transformers. And since then, right, things have just gotten more diverse and more exciting. And that kind of summarizes the high level, how physics started to evolve. And you can see this in the performance, right? So our ability to kind of reduce our background, started from kind of like simple high-level ML to reduce the background with more technology. We got a factor of 3 or 4 in background reduction with the same signal efficiency, and then another factor of 3 or 4. And then finally, things started to saturate it as you get to transformers. So this is my approximation of it. And now we see it all over the place, right? So it's kind of everywhere in the experiments, right? We're using it in a lot of things. And we're starting to see lots of physics results, right? So just to give you an idea, right, here's a physics result that used kind of very simple machine learning on the left. You can see this peak here. This is a W boson, so the weak force mediator. And here's the same analysis now with more data and deep learning, and you can see you can dramatically reduce the background and make a very large, very significant peak here. So deep learning is really changing the kind of quality of the things that we can do. It's also allowing us to kind of diversify the scope of things that we can do. So we can see here we see W boson peak, but with the same neural network, we can actually isolate, in this case, this red guy are Z bosons, right, decaying to B quarks. And you could zoom in here and actually look for a Higgs boson. So there's lots of things that we can do. So this talk, I'm going to talk about how AI impacts high energy physics. I'm going to go broader. I'm going to talk about what we're doing. I'll touch a little bit on LIGO, how we can use this for gravitational waves as well. This is by no means comprehensive, but I'm just going to highlight various different things. So here is where everything is centered. We start at the Large Hadron Collider. This is what it looks like. This is like Geneva. This is the city of Geneva over here. And here's the ring, right? This is what you see if you go hiking in the Jura Mountains. Go over there. And what do? We have these very massive experiments, right, where we take a huge amount of data, right? This is the experiment I work on, the CMS experiment. There's lots of blood, sweat, and tears here. All these, like, you can't even see it, but these little green things, I actually connected them. I spent a big part of my PhD connecting cables, or enough of my PhD. And ultimately, what do? Well, we collide, and then we look at these collisions. So let me share my screen, and I'll just give you a short animation of what a collision looks like. So here we go. So I think I can full screen this. All right, so here's a collision. So the collisions come in, and then you get particles, and you get sprays of particles. The histograms here are energies. This is large sprays of energy. And there's lots of different detectors here. And the kind of particles go through all these detectors. They leave hits, and then we link all the hits and collect them into particles. And then we see flows of energy, and then we use this to analyze. So that's basically how a particle collision looks. And that's basically how we start to analyze the data. Sharing. Okay, so what does this mean in practice? Well, here's a collision. And you can look at this collision and see lots of different things. So I can see kind of an energy flow here. This is like this green bump here, another one here. This tells me that this is a kind of a cluster of objects, and it has two kind of cores, right? Clusters of objects like this are what we call jets. They're typically from quarks and gluons. And the fact that this has two subcores actually means that maybe it's from a resonance, right? Something like a Higgs boson, right? So we could identify it. And this is really effectively what the challenge is of doing analysis. So what we do is we take our kind of raw hits, we connect them into particles, and we link these to different, we have a collection of particles. Then we take the collections of particles and we start to look for aggregate properties. And to understand this, well, imagine you take the path of a quark or gluon. It will shower to more quarks and gluons, which will subsequently shower to more quarks and gluons, which will subsequently shower to more quarks and gluons. And this showering is not what you would think. It's not a kind of a tree structure. It's a quantum mechanical shower. So these things are all interfering with each other, right? So there's a wave-particle duality you have to keep in mind. And ultimately, you see particles at the end. And these are what the collisions look like. This is what I just showed you in the animation. And the challenge for us is to go from these raw particles here on the right to actually the original kind of collision that we care about. Like in this case, let's say it's a gluon. It's showered to all these particles. And so this is the kind of idea. And this is where kind of machine learning plays a great role, especially when we're talking about very large amounts of particles. So typical collisions at the LHC can have, like the core collision can have hundreds of particles. And in fact, you usually don't just collide one particle at a time, right? We collide, in this case, about 60 to 70 protons at a time. And so you have another kind of 4,000 particles on top that you have to remove. Right? And so our challenge here is to take the particles we care about, extrapolate to the center. And we can either do this simply by trying to sum up the particles, like sum up the vectors, and then use high-level observables and extrapolate. Or we can take all the information with machine learning, right? And that's really the challenge. Now, I mentioned, right, we don't just collide one collision at a time. It's typically 60 at the moment. In the future, it will be 200. And we have all these clever strategies to isolate the collision we care about. And in fact, one of the things I did was I created the puppy algorithm. right? Which is a rule-based algorithm that actually removes, most of these particles. So you can go from the kind of 4,000 total particles down to like the few hundred that you care about through the puppy algorithm. So it's not a machine learning-based algorithm, but it's kind of like that. Now, the other thing to keep in mind is that we collide at an incredible rate. So I just showed you one collision. A collision is about, 8 megabytes of data. We collide 40 million at a collision, 40 million clumps of protons per second, so 40 megahertz, right? And so if you were to kind of translate this into data, right, you're talking about many exabytes a year, right? So this is more data than any other device on Earth. The data rate is, about a factor of 10 or 100, depending on how you count, more than any other device. And we're talking about kind of data rates that are on the order of, rivaling a petabit per second. Now, the thing is, because the collision is a high radiation environment, you actually need to analyze the collision as fast as you possibly can. So we're kind of restricted to 10 microseconds to actually do the first analysis to save the data going down the stream. So it's a kind of enormous amount of compute, much more than you would have from Google or from Netflix or these other things. Right? So it's really incredible. So the kind of theme for this is we're going to kind of look at how ML algorithms can kind of isolate things that we care about. And I'm going to start with kind of fast algorithms where we do very quick cursory glances at their collisions. And then I'll talk about slower algorithms that are more complicated as we go. All right. So let's talk about fast machine learning. So we take data, 40 megahertz. We then kind of filter the data. We look at it very quickly. It's like kind of coarse, fixed bit precision data. And we filter it down to a rate of about 100 kilohertz. So we select one event in 400, and then we pass it to the next stream. We then subsequently filter it again. We select one event in about 100, and then we save that to disk. Right? And that's the kind of tier for how do we actually collect data at the LHC. So in the first two, you have to analyze data as fast as you possibly can. Right? And so the challenge here is that because you have to these kind of very restrictive constraints, you have to do this on custom electrons. Right? And so the way we do this is we use special processors. And just for scale, right, we're talking about 17 yottabytes of data per year. So it's about 100 internets worth of data, right, per year. So that's the kind of scale. And so the idea then is we look at all these collisions, and then we want to select fractions. This is what the green guy looks like. And ultimately, this little red fraction is actually the fraction that we save. So this is the kind of scope of data that we actually analyze offline. We make discoveries on. The rest of the data we throw out, right, completely. And so what data are we throwing out? Well, typically we're throwing out kind of the low energy collisions. Typically these tend to be the least interesting. And so what we'll do is we'll make this kind of fast analysis, look for the high energy or the interesting feature collisions and save those. But the low energy ones, right, that occur at high rate, we throw away. And kind of in our intermediate tier, we try to analyze, some of the kind of intermediate energies. Right? But we know that at low energy, right, there's lots of exciting, interesting physics that we care about. Now, just to show you an interesting one, here's a Higgs boson. Right? So this object here is actually a Higgs boson candidate. And it just passed our threshold of saving to disk, right? The threshold's at 450, for this is the momentum of the jet. And had it been below the threshold, we would have lost it, it would have been deleted, and we wouldn't have been able to study this, right? And so we lose kind of precious events every day, at an incredible rate. So the challenge then is to kind of see if we can improve this quality. And so the way we do this is we program custom electronics, and we do this on field programmable gate arrays. So what is an FPGA, right? FPGA is a special chip where you can program all the different elements of the chip. And so the idea is you can think about, like you have your chip, you have all sorts of programmable elements, and you can put your algorithms, you can unroll them on the chip, right, for processing, right? Programming an FPGA is akin to kind of writing a score for an orchestra, right? So you imagine you have a beat, that's your clock, and you're going to try and take the whole orchestra and write, different parts for the orchestra, and everybody's going to play at the same time, right? That's kind of, and you can imagine, right, FPGA is like, you go to see a big concert, like a Mahler or some huge orchestra, you have to sit and think about how everybody's going to fit together, right? Programming a CPU is quite the opposite, right? You can do very complex calculations per clock, but you just have one stream, right? There's just one player. And a GPU is like somewhere in between, right? You're kind of giving the band a set of instructions, right? The same instructions, right? Just play along. But then you can feed it different data streams, right? So it can kind of do some level of parallel computing, right? So for our purposes, GPUs and CPUs are just too slow, right? And they might have arguably more compute, but you need to use custom electronics. And so as a first task, when we were starting to do this, we wanted to just make a rule-based algorithm. And so we made the algorithm called like particle flow and puppy. So it's an algorithm to kind of take all the raw particles, collect them into particles, and then isolate the collision that you care about. And so we implemented this on an FPGA. And just to show you what it can do without telling you the details, it can take all of these raw hits, collect them into particles, isolate the collision, and reduce it to these kind of events, right? And a tuned, collider physicist would see this and say, oh yeah, that's a top pair production event, right? You can see there's 6 quarks here. And so, what we've done is kind of run a very complicated algorithm, but heavily parallelized, and we've done this on a chip very fast. And so this takes 690 seconds. But after we did this, so we got excited about doing this about 2017, 2018, and this took surprisingly little amount of time. So we decided to see how far we could push it. So we said, well, what if we could add deep learning? Deep learning had never been done at this kind of speed, right? So in order for us to do kind of this level of analysis, you need to run algorithms at the kind of sub-microsecond level. Deep learning had been kind of targeting humans, right? And so human response times are kind of in the order of milliseconds, right? If you speak, you can speak at a rate of about 5 to 10 hertz, right? So it's 100 milliseconds. But the LHC is running in nanoseconds, right? So 1,000,000 times faster, right? And so you have to actually be able to have algorithms that can run at this speed. And so we asked the question of, could we bring deep learning to the LHC and deploy it in real time? And so we made a software called HLS for ML. Oh, sorry, I'll just skip that. I give a similar summary at BU. That was one of my postdocs. And so let me illustrate how HLS for ML works. So let's say I want to take a very simple neural network. I take 2 inputs, I have 1 output, and I want to kind of do a neural network processing on that. Well, what do? I take my 2 inputs, I multiply each of these by a weight, I add a bias, and then I apply an activation function, and I get my output. So this is a 1-layer, very simple neural network. However, on an FPGA, we want to make this run as fast as possible. And so what we have to do is distribute the computation. So what we can do is split it. So we can have our inputs come in, we do our multiplications in parallel. We then add them, and then we apply an activation function in output. On an FPGA, this is done at a clock level. So you can imagine at 1 clock, right, you do your multiplications. The next clock, you do your additions. And then the next clock, you get your output. And not only that, you can put this at different parts of your chip. So you can actually pipeline this, right? Oh, sorry. So I can actually feed in my next set of inputs every clock. And so this is a neural network that takes 1, 2, 3 clocks. And it can take a new set of inputs every clock, right? And this allows me to actually run a kind of machine learning algorithm very fast. And so you can imagine scaling this up to many inputs, to kind of many multiplications, many layers of a neural network. And you can see this becomes very efficient. FPGAs are typically clocked at the hundreds of megahertz level. So we're talking about neural networks that can run, in this case, right, this is a neural network that can take a new set of input every clock. So it can run at 250 or 300 megahertz, right, which is enough to actually start processing collisions. Now, how does this translate? So we can take a little more complicated neural networks and do this to actually look at events. And here we have we made a neural network that can do sort of so-called B-quark tagging. Why is B-quark tagging so interesting? Well, it allows us to measure the Higgs self-coupling, which is like one of the fundamental parameters we want to measure at the LHC. And we found that this neural network was able to kind of double the acceptance of Higgs to Higgs boson events, double our ability to select 2 Higgs boson events with the same kind of background rate. And so we were able to kind of double our number of events. This translates to actually something like an improved measurement in the Higgs self-coupling of about 30 to 40%. And I won't go through the physics, but the Higgs self-coupling tells us about the stability of the universe, right? So it's a kind of very fundamental thing. There's lots of other algorithms I can show you where we can kind of dramatically improve things. And here's for tau lepton identification. This is another algorithm. And you can see we can reduce the background by something like an order of magnitude, while at the same time increasing the efficiency, right, for our selections of taus. So it's pretty dramatic, adding machine learning at this level. And the nice thing is that, since then, our library HLS4ML has now become the standard at the LHC for real-time processing. And there's algorithms already running. So there's an AI anomaly detection that's running in CMS. And there's one actually in the ATLAS experiment, as well as a displaced muon neural network as well. So we're running this all over the place. OK. So this is our software toolkit. It's become kind of the standard for super fast machine learning algorithms, right? And after we did this, we realized that nobody else had kind of solved this problem. But people actually do need really fast or sometimes low power machine learning algorithms. And so we've kind of gone on a quest to see where lots of other things see what else can use it. And so we made an organization called the Fast Machine Learning Organization. Now, to give you some insights of how we actually use this, let me kind of walk you through kind of the kind of ways that we work with neural networks, right? For this under this fast machine learning paradigm. So let's say I have a network that needs to analyze data, and I want to like shrink it and make it work as fast as possible. Well, the first thing I can do is I need to capture the kind of problem I want to care about. So here I have a horse, and I want to identify this image as a horse. But there's a lot of other stuff going on. So I can try to make my horse, make this a simpler problem. So the first thing I can do is I can, blur it. So I can just reduce my data rate. This is something we do on the FPGAs all the time. So I can make a fixed bit precision neural net that can analyze it. That already reduces things. I can also try to take my horse and I can remove the background, right? So I can sparsify my data set and preserve only the info I care about. I can also, take my horse and kind of cleverly sparsify, just dealing with the boundaries in this case. And you can still tell it's a horse, right? I can go even further. I have to be careful though, right? If I start sparsifying, I start really cutting the data, and I want to recover, I have to be careful about how I recover. So imagine I were to AI in-paint this data. Well, I would get a new horse, right? This horse looks pretty nice. But if I'm careful, right, and I compare these two horses, my original horse, a beautiful stallion, my horse on the right has like, the most perfect coat I've ever seen. Right? So it's maybe too beautiful. And so you have to be a little careful about kind of overdoing it with your kind of compression algorithms on your chip. But suffice it to say, this is a way of making algorithms much faster. And so this kind of scheme of quantification, sparsification, and kind of very clever sparsification is what we do on the chip to make our algorithms run really fast. And there's one last thing that I think we find, that we can do even better is we start to use symbolic learning. And so here I have a Picasso horse. This is a Picasso. Picasso famously drew these paintings with just one pen stroke, right? And so here we have effectively an analytic function that describes my horse, right? So this we can think of as a kind of symbolically learned data set. And physics data is perfect for this, right? There's lots of symbolic learning is kind of very efficient. It's a nice way to capture data. And we've been playing with these methods as a scheme of compression and putting them on FPGA. And we found that these kind of dramatically reduce our ability or dramatically reduce our compute. And so to give you an example of what I think is like the biggest compression, we started playing with these Kolmogorov-Arnold neural networks, right? And what they do is effectively they take data and they use splines to kind of interpolate over the data. So in this case, they use B splines. And we can then embed this in a neural network. Where we use the B splines as activations, right? And we can then embed this onto hardware and actually kind of compress our data. And it turns out that splines are perfectly replaced on an FPGA with lookup tables. And so we can take our splines, turn them into lookup tables, and then we can embed the full kind of Kolmogorov-Arnold network, which is just a collection of splines and kind of layers, like just normal weight layers with weight 1, and embed this on a neural network, and we can make a new super optimized algorithm. And so we actually made something called CAN-LA, which we call it, it's based on can, so we call it CAN-LA. It's named after the small French sweet pastry. And this can actually compress algorithms super efficiently. To kind of give you the idea, our baseline algorithms that we currently have running on the LHC, they would take up something like anywhere from 10 to 30% of an FPGA. We can get the same performance with these CAN algorithms with about a 30th or even 100th of the amount of compute. So you can dramatically shrink the algorithms. And this work is recognized by the whole FPGA community. It's often viewed as the most efficient way to kind of compress algorithms. We just won the best paper. And to kind of give you an idea of how much this reduces the compute, we can take an algorithm. So this is an algorithm for, in this case, toy car identification. And you can see that we reduce the amount of compute by the number of kind of LUTs and flip-flops by a factor of 2 or 3. But for the same algorithm, we can run, we're about 1,000 times faster. So we can kind of run 1 million inferences or hundreds of millions of inferences per second compared to like hundreds of thousands with our kind of previous algorithms, right? So these are, ends up per inference ends up being incredibly energy efficient. Our latencies are incredibly fast. And so this is one of the schemes that we've been using to kind of embed things on FPGAs so that they're very efficient. Right? And so I'm just giving you a high-level example of one of the many things that we've kind of been doing to make things run fast. Now, our toolkit, HLS4ML, is kind of all over the world now. We've run it with very large models. So I did an example with some guys at University of Toronto where we made a neural network with 50 million parameters distributed across 20 FPGAs. This had the fastest, at the time, the fastest batch 1 ResNet 50 inference time in the world. We've done this now for things like cell therapy, so rapid identification of cell in the blood. So you can kind of identify cells in microsecond timescales and tag them, right? We've also used this now for quantum computing. So we're actually in the process now of deploying our algorithms. It's been deployed on a quantum computer, and we're looking at kind of new ideas to do this, deploy this in quantum computers. And it's also actually being used on phones. So if you use your image identification on your phone, a lot of this now uses our software, which was developed for high-energy physics collisions, right? And actually recently we're very close to actually running a kind of brain-body interface with the same software. So this is kind of an example of where something we did in high-energy physics that has lots of applications. And a lot of the insight has been actually bringing in kind of physics-informed, like neural networks that are like, or symbolically motivated neural networks that we find to be very expressive and allow us to do things at very low bit precision with very high accuracy. There's lots of exciting things to do there. And so out of this, we got very excited when we started this. We made this organization called Fast Machine Learning. I'm actually the chair of the Fast Machine Learning Foundation. We are a nonprofit aimed at kind of cultivating lots of applications for low latency, low power inference. All right, so now let me switch topics, and I'm going to share my screen. Actually, are there any questions?
I don't see any at the moment, Philip.
Okay, so I'm going to switch topics and talk a little bit more about kind of larger scale machine learning that's not as, let's say, bespoke. And so I have a bunch of animations. So let me see if I can, let me share my screen. All right, I think, hopefully I'm sharing. Okay, good. All right, let me, so I want to now illustrate a little bit of what we do, what we typically do offline. So when we try to make neural networks offline, we're often trying to kind of look for kind of subtle deviations in the data. And I want to illustrate a tagger. And I'm going to illustrate a very simple tagger, but it's going to have all the kind of properties that kind of we care about when we search for new physics. And so I'm going to make a data set where I take some happy cats and some sad cats, and I'm going to embed this into like an image. And I'm going to let your eyes kind of discriminate these images. And these cats are going to have different colors. So here's my data set. So, so you can see this is the data set. You have a kind of rainbow color of cats. And there's a hidden message in here with happy cats. So if you look very carefully, you might be able to see it. But it's kind of hard. So what we can do is we can filter our data. So we could imagine applying a rainbow filter. That gets rid of our kind of cat image our cats, and we just get happy and sad faces. We can go one step further and take the rainbow colors and just decolorize. And so now we can start to maybe make out a message if you just look at the red aspects of this image. But there's still lots of kind of distractions here. So we could take our gray and turn it to black. And so we can take it black, and suddenly you might be able to see a message, which might be the logo of my institute. Well, what did I just do there? All I did was I took your neural networks, your eyes, and I decolorized them. So I made it just one color, and out of that I was able to kind of give all this noise, right? And suddenly you're able to see an image, right? A hidden image. So what did I do? Well, this is effectively what we have to do when we start to look at collisions. So often in the case of particle physics, we're looking for bumps, right? So we're looking for resonances at different masses, right? And you can imagine mass is your color axis here. And so what we're doing here is we're blinding our algorithms with respect to mass. And so it turns out blinding algorithms with respect to mass has been the key insight to kind of our ability to deploy kind of machine learning algorithms at large scale to analyze collisions. And just to give you an idea of something that we did, here's a first kind of very simple algorithm. This is actually not, there's a little bit of machine learning here, but it's basically a rule-based algorithm that we made that was mass blind. And we could see this process here, the W boson to quarks. This is a process, by the way, that before we did this, everybody thought was impossible to see at the LHC. It's a very hard process to observe. And once we made our mass blind neural network, we're suddenly able to get this very high resolution, very clear signature, right, with lots of events. And so this is kind of the way technology has evolved. And the key insight has not been just the kind of deep learning technology, but it's how do we bring this into the physics world? And in this case, mass blinded neural networks was the scheme. So, variations of this are things that you probably hear about with, LLMs when you talk about alignment, right? Here we're asking a neural network kind of a similar question, a much simpler question in some sense, is how do we make sure that our network is not biased, right? If I were to not take this network and not make it mass blind, this background would not be smooth, and I wouldn't be able to control it, and I would be looking for a bump, probably on top of a bump, and you wouldn't be able to see it. And so allowing our ability to make mass blind neural networks has really enhanced our ability to kind of do lots of different new physics searches. Right? And so that's been one of the key insights. I won't go through the physics results, but suffice to say there's a huge amount of results that have been done on this. Things that measure the Higgs boson, things that measure search for dark matter, lots of other things. All right, so now let me do another kind of algorithmic idea that we're using. It's very popular, which is AI anomaly detection. And so let's take the same data set that I had before. So we have this data set, and you see these like fun colors here, right? What is all that colors? Well, to illustrate what those colors are, I want you to kind of learn them. And so to do that, I want you to take these two images here and try to find the differences. Right? So this is a Van Gogh, right? You probably all know it. And if you look carefully, you'll see that these images are different. So you might notice, I don't have too much time, but you might notice up here, there's kind of two stars. Here, there's not. And there's a few more differences here. Right? In fact, there's a difference over here, right? And so, well, what did I just do? I made you look at Van Gogh, right? And so now I can tell you, well, why don't we look at these other photos, these other paintings? And you can look at these, and I asked the question, well, which one of these is Van Gogh? And you can look at, based on your previous knowledge, that, well, maybe this one is not, maybe this one's not, this one, but this one has the same kind of light and paintbrush structure that you would have seen before. And so what I did is I gave you an exercise where you looked at images, right, and you try to compare two images. And then by virtue of looking at these two images, you learned kind of a residual feature of, what are the qualities that make a Van Gogh painting. If I had given this to a computer, I would have, what would it have done? It would have taken the kind of left image and the right image, overlapped them, subtracted the pixels, right? And it would have seen the differences, right? But if I line them up pixel by pixel and take the difference, I'm not learning about Van Gogh. I'm just learning about the differences between these images. And so the key insight here is that we want to actually teach an algorithm to learn physics. And so we want to come up with training strategies where we actually kind of give it tasks so it can actually learn physics, right? And there's a kind of bunch of literature on this. And I'm just going to highlight a few things that I've done. So one is we first decided to train neural networks, so in this case, autoencoders or normalizing flows, that compute the probability that a data set is from a certain object or a certain process. So you can imagine a background process, and then a signal process, and these are two data sets. And I can make an axis here where on the left is a high background probability, and on the right is a low background probability. I can then train another neural network that computes probability of a signal, and on one side is kind of high probability of signal, and on the other side is low probability of signal. And then I can kind of embed these into a 2D space and make an embedded space. And so out of this, the signals are going to be on the right, and the backgrounds are going to be on the left. And then the kind of in between, there's going to be lots of kind of anomalies, right? Or things that are not signal or background. Right? And so now we have this kind of interesting embedded space. This turns out to be a great space to actually search for new physics, right? So if we had a true signal, well, in reality, true signals are probably going to have properties of hypothetical signals. And so we can imagine looking in parts of this space, perhaps the right corner, to actually look for new physics, right? And so we can go ahead and take this same data set and actually do the same learning principle. And we can kind of move these. And we let this evolve. And what you'll see is that exactly this is what happens, right? On the top left, right, you have sad cats. On the bottom right, you have happy cats. And now you start to see your anomalies pop up kind of in these different diagonals, right? In fact, the bottom left diagonal tends to pick these up. Well, we could actually generalize this even further. We can take an image and just augment it. Doesn't matter what the image is. So we could take a cat and augment it, just give it glasses. We could take a dog, augment it, just give it glasses. And out of this, we can then try to make a space. And what we'll do is we'll say our cats and our augmented cats should be in the same part of the space. And our dogs and our augmented dogs should be in a, kind of the same part of the space. We don't actually know what a cat and dog is. We can go over the whole data set and stretch it out so it spans the space. That effectively maximizes the distance of everything with everything. And out of this, we get some learned order, right? Some sort of task emerges where the cats live on one space, part of the space, the dogs live on the other. And we can kind of completely do this with, particle physics. And so I'm going to take my same data set, and I'm going to give it a task now where I just translate it in X and Y. And so this is a shift symmetry. Shift symmetry, if you know physics, is just another way of saying conservation of momentum. So from Noether's theorem, this is a symmetry. And what we can do is we can just apply this shift symmetry into our data set. And this is effectively making our data set colorful. So we can go and see what it learned. So now this is train it. It trains. And then we get this data set like that. So we get a new space. Well, we can go in this space and we start to see order, right? So here on the top left, we see kind of sad cats. The bottom right, we see happy cats. So we've kind of separated our two classes that we care about. But we've also managed to find all the strange cats, right? The cats that are multicolored, right? They live in a different part of the space. And we didn't actually know anything beforehand about this data set. We just shifted it, right? And then we said, well, we want to have shift symmetry in our data set. Right? So this is the same as saying, in this case, color invariance in our data set. Right? And out of this, we've learned some order, right? And we've been able to classify the different objects. We can take the same idea and generalize it to physics, right? We can replace our cats with Higgs bosons and our dogs with quarks and gluons, and we can start to learn actually what these things are. I think I'm done with animation, so I'll go back to the slides. Here. All right, and so what does this mean in practice? All right. So what does this mean in practice? Well, in practice, this means we can go ahead and train this. So we take a Higgs and a quark and a gluon. So here's a Higgs, and then the blue is like a shifted Higgs. And so in this case, the way we're going to shift it is we're going to reshower the particle. So we're going to take the same object, and we're actually going to let the particle reshower. What does this mean? This is the right way to think about this is from quantum mechanics. So you have a wave function, and every time you shower these particles, you're collapsing the wave function. And so what we're doing is we're saying, well, the full wave function should be embedded in our space, right? So we're not going to collapse it. And so what we'll do is we'll take the object, collapse it and then collapse it again, and every time we collapse the original object, we're going to say that the original object and the other collapsed object should live in the same part of space, right? So we're trying to embed some notion of quantum mechanics, right? And we're doing this by effectively just reshowering our particles, right? So here's our object, and the blue is a reshowered of the red. This is for Higgs, the right is for a quark. And now we can make an 8-dimensional space. This is what it looks like. And we can project it down to 2D. And this neural network did not know anything about what a Higgs or a quark or a gluon was. But if we look at the 2D projection, it's already able to kind of separate these things out. So you see the Higgses live on one side, the quarks and gluons live on the other. And even the quarks and the gluons themselves are separated, right? So despite not knowing anything about particle physics, we're suddenly able to kind of learn how to compact it. So, we can then translate this into kind of new physics searches, right? This turns out to be very powerful. It turns out to be invariant to kind of our modeling uncertainties. And we can get something like 25% gains over state of the art, right? Or if we just look at kind of training Higgs against background, but even if we go out of domain and try to do other tasks, right? We can get another like 10% gain on top of a conventional machine learning algorithm. So, but this also means that we can start to think about training on all of our data sets all at once, right? So we can make big networks that actually start to learn all the physics simultaneously, and then we can go ahead and search in that space. Well, what are we doing? Well, we're taking something that looks from raw data. We're using these kind of symmetries of physics, compactifying it, reducing the data sets, and now actually searching for physics in this new data set. And so, in fact, here's an idea where we took that space, compactified it, and then searched for new physics. And we search for a new particle, and the separation from our raw data is that the kind of the separation between green and purple. Purple is with no signal, green is with a signal. And you can see if we look at the raw data, it's this 57-dimensional space, right? We can't really separate green and purple. But now after we compactified it into 4 dimensions, right, using a symmetry, right, we can suddenly separate out the green and the purple. They're kind of very clearly separated. So you can actually start to discover new physics if you know cleverly how to compactify your data. And we've been able to generalize this to many domains. So we did this for the LHC, but we've also generalized this to gravitational waves, right? Where we go from very high dimensions down to a few dimensions. What does this mean? Well, it's kind of changing the paradigm of how we do physics analysis. So like in the old days, 10 years ago, we would go to theorists and they would give us some rules, physics rules, and kind of give us some dimensional space. And it would reduce our dimension down to like an AT space. And we would use we use these rule-based observables to search for physics. Now we're in a domain where we can go to a theorist, ask for symmetries, right, and build a neural network that actually learns how to capture the physics. And we can do the same searches and in fact improve our sensitivity. Right? And just to show you, right, we've been able to discover the Higgs right this way. So I'll kind of skip these details. But here's a case where we actually found the Higgs boson, right, without actually telling this data set the Higgs boson was in there. So we just said, find the anomalous features in this data set. And so it did a kind of generalized pre-training strategy using symmetries and physics knowledge. And then we're able to find the actual Higgs boson without actually telling it anything about the physics. Right? So it actually just, these are the most anomalous events right, on the y-axis. Right? And you can see these kind of anomalous events are all at the mass of the Higgs. Right? That's real data. So, I mean, what have we done is we've kind of taken the scientific method, right, where we observe data, inquire, and we systematized it, right? And we systematized it into an algorithm where we basically start with some data set, we learn a space based on our knowledge of symmetries and our knowledge of physics, and then we can actually use that space to actually look for deviations from the normal, right? So do anomaly detection. So this is an algorithm we call AutoSciDAC. It's a kind of automatic AI discovery tool. And we've applied it now not only to, it's differentiable, we've applied it now not only to high energy physics, but to kind of many domains, right? Yeah, here's a version of a kind of anomaly detection we've done at the colliders, right? And suffice it to say, we didn't see anything, but we were able to, with one algorithm, kind of exclude order 100 different new physics models, right? And here's the kind of performance. Sorry, I don't have the performance, but we can take the same idea and actually apply it to many different science domains. And it turns out to be, close to optimal in many cases. All right, let's see. I have kind of two things I should talk about. I'll try to go quickly. So one other thing I want to mention is that a lot of this now we're doing for not just particle physics, for multi-messenger astronomy. And the reason we want to do this is that we'd like to use gravitational waves to kind of look for events and then alert the rest of the physics community that something is happening. This is what we call multi-messenger astronomy. Turns out gravitational waves, if you have, for example, an astrophysical event such as a neutron star merger, you will see it first in gravitational waves. And then you want to tell everybody else that there's an event. And so in the case of LIGO, right, it's an all-directional experiment. And you want to actually tell the telescopes to point in a specific direction because there's an event. Given that, right, we actually, a few years ago, started working on a way to make a kind of real-time AI-based alert system for gravitational wave data. And so how does this work? I forgot there's animations here. I guess I'll share my screen again. So how does this work? Well, you take 2 time series data in, and the data comes in, and then you want to make a neural network that looks for any deviations right from the data. And so here you're going to have a black hole merger. Comes here, you can see it. And the idea is that once it's here, you want to make an alert. And so we made an end-to-end AI pipeline that will do this. It will clean the data. It will then look for events, right? And then it will determine what that event is interesting. And we've now managed to kind of completely replace the conventional algorithms with doing this. So we may have an algorithm that will denoise. So the orange is the clean data. The blue is before. Right? This is just showing you a snapshot of the data. You can see it's denoised. We have an algorithm then that will identify black hole mergers, and we're adding kind of neutron star mergers. And so it looks at this data set and computes the probability that there's a black hole, right? That's what this green score is. And this turns out to be able to probe more of the universe than any conventional rule-based algorithm, at least for heavy black holes. Right? So this is the volume of the universe you can probe. This works on data. And we have, in fact, an algorithm that takes this time set and on top of that tells you where in the sky this is located. And the big advantage of all of these algorithms is they run really fast, right? So the kind of conventional rule-based algorithms can take about minutes to run, whereas these take about fractions of a second. So we're talking about things that are about 1,000 times faster. You can then imagine generalizing this to anomaly detection. So here's an algorithm that builds a 8-dimensional space that you can probe and look for things that are not normal, right? We didn't see anything, but it works. And all of this now we've embedded into a real-time system that is currently operating. And it's been operating since August 30th last year, right? It's making alerts. Here's an alert. And just to show you, right, once we turn this on, we pretty dramatically sped up our ability to look at gravitational waves quickly. So here's the first event we found. A-frame is our algorithm. And you can see the first alert took 24 seconds. The actual kind of machine learning part is about 1 second of this. Most of this is like shuffling data around. And the kind of conventional rule-based approaches took something like 10 times longer. So they weren't limited by shuffling of data, right? They were limited by the algorithmic computation. So suffice it to say, machine learning is kind of dramatically increasing our ability to kind of do compute and run things fast. All right, so there's a whole kind of scheme of how are we going to deploy this on scale. But let me kind of end this talk with a paper we put out a few weeks ago, which is we asked ourselves the question, right? We have all these AI algorithms that are doing lots of things, but we're kind of embedding them into kind of conventional physics-based analysis. We asked ourselves the question is if we could slop until we drop, right? So if we could actually do a full AI slop-based analysis of particle physics data. Right. Now, suffice it to say, people are trying this all over the place, but we tried to take a very systematic approach to this, and we wrote a paper. It's 500 pages. So 520 of these pages are AI slop. Right. We did not touch at all. And then there's a 20-page kind of statement paper about how we did this, and we effectively made kind of AI-assisted workflow that does all of the steps that we would do internally in an analysis for particle physics, right? And all we did was we had Claude, talk to a bunch of feedback robots. review the context, and then we kind of adjusted our context and do the kind of analysis. Right? Here's the structure of how we did this. So we had some schemes. We had like a RAG that integrated these things. And importantly, we had this kind of gated inference scheme where we ran our analysis. We had feedback bots kind of feedback and iterate back and forth doing the physics analysis. We gated our results. So we did we had a human gate. We looked at 10% of the data. So we did a 10% unblinding of the data. And then we had a human look at the results and decide whether it was time to actually look at all the data and perform the physics measurements. And so that was kind of key, because then we would, the human would look at it, give feedback, and then we would iterate a few times. And it turns out, to our surprise, right, a relatively simple structure like this, with kind of just using heavily Claude, we were able to kind of put out, nearly publication grade results. So we released our paper with something like 10 different analyses, and if you look at V2 of the version of the analyses, right, they're actually at the level of, like, I'd say a 5th or 6th year grad student. So they're kind of actually pretty good. And they're doing classic measurements from our field, like the Z-width measurement. So what does this mean? Well, it means that we can start to think about bigger and bolder research, right? Inside the collaboration, there's all these like kind of schemes for internal review, right? Kind of cross-checking, telling you to go run these very tedious cross-checks before it can leave the collaboration and go for publication. This allows us to kind of avoid this scheme, right? And so suddenly we can actually streamline the whole review process, right? We can do very quickly, high quality physics work. And ultimately this starts to make our students feel more like postdocs or professors, right? Where, I tell my students, go do this work. They show me a plot. I'm like, this doesn't make sense. Go back, fix it. And they iterate back and forth, back and forth. Now we can imagine, having students really discussing doing that step with the AI, and then coming to me with things that are, actual physics results. So I like to call this world Super Dario world, just because we use Claude, and Dario Amade is an old friend of mine. So this is kind of the way we envision the future. But the big thing is that it replaces the many tiers of review that we currently have. So if you're interested in more of my stuff, go to fastmachinelearning.org. So this is the kind of organization we run. You can hear about my institute, where we do real-time AI for gravitational waves, LHC, and so on. There's something at CERN called the NextGen project that's built on these ideas. We have a machine learning challenge if you're interested. I have a course on kind of computational data science and how you apply it for physics data. And just to summary, right, we've kind of had a vision that AI can be deployed and kind of allow us to do kind of finer grain, more detailed, more complicated physics analysis. We see that's making things run. We can run things much faster. We can do things in higher detail, right? But we still kind of need the human in the loop, right? And so if I were to take this image here, which has our logo of my institute embedded in it, and ask it to AI, do you see the message? It still misses the big picture. So there's still time for us to be clever, but the time might be getting short. So just a thanks to my group. So thank you.